Hello, you are now entering the infinite void. Hang on tight. We cannot save you now.
Hello and welcome to this week's episode. I'm your co-host Matty.
And I'm your co-host Jacob, and today's episode is our Halloween special, and it's all on paradoxes. I was trying to figure out how to title this episode this week, and it was really difficult because I was like, can you call it? Is even paradoxes even a word? But apparently it is, and that's where we're going. So paradoxes.
Very spooky.
Yeah, very, very spooky. We spent a couple of weeks really trying to figure out what we wanted to do for our Halloween special, because I think for our last one we did kind of like the worst outcomes, I think it was. So we kind of just broke down like asteroids hitting the planet, natural disasters, AI taking over. I think we talked about the whole grey goo thing and all of that kind of stuff, which was super depressing and existential. But this time we thought we would try and melt everybody's brains really and look at some interesting paradoxes that we find fun to talk about and discuss, because if there's one thing that this podcast likes to do, it is a thought experiment on something that will bend your brain a little bit. So me and Matty have kind of gone away and we've picked some different ones and we're going to kind of be breaking them down today. But for anybody that doesn't really know what a paradox is, it's basically kind of like something that kind of goes against itself, right?
Mm-hmm. Yeah, I see you give me your excellent notes, which I forgot to type up this week. But you said there's different types of paradoxes, but fundamentally a lot of them rely on some sort of like contradiction within themselves. Yeah, they don't make logical sense.
Yeah.
Anyway.
Yeah,
so.
and like you said, that's one of the types. So you've got logic, mathematics, decision theory, which I'm not sure what decision theory is. Is that just decision making? And
one of my ones that I'm going to talk about is related to decision theory.
Okay, so I will find out then. But then you've got physics, biology, chemistry. Obviously, I'm going to be interested in ones to do with time travel. And then you've got philosophy and mysticism. But thought we'd kick off the episode with one that is pretty well known, and that is Schrodinger's cat. If you follow me on Twitter, I tweet out this quite a lot, and I make some jokes about stuff that I'm doing when things all to do with existing and non-existing. But essentially what Schrodinger's cat is in quantum mechanics, Schrodinger's cat is a thought experiment that illustrates a paradox of quantum superposition. Not superstition, it is Halloween, but it's superposition. In the thought experiment, a hypothetical cat may be considered simultaneously both alive and dead as a result of its fate being linked to a random subatomic event that may or may not occur. So am I right in saying that this kind of comes on from the double slit experiment, where if you're not looking at something, it is in like a probability field where it exists and doesn't exist in multiple areas or in a area, and then when you're observing it or when something's being observed, it exists outside of a waveform. Am I right?
Yeah, so fundamentally, and we can come back to the cat and sort of real life later, but at a quantum level, when you're talking about classic thing, it's like an electron going through a double slit, or around an atom, if you studied any sort of chemistry at A level. At that sort of quantum level, things aren't like the billiard balls that we think they are. They are not solid things that do stuff. They are defined by, as you put it, a probability field, this wave function. And you can't really say that something is somewhere or is doing something. You can just say with a certain probability that it is somewhere. Yeah. So when talking about a double slit experiment, you can't say that it has gone through one slit, it will go through this one slit or go through the other one. You can just say with a probability of what has happened until you observe it. And the observation of this is where it gets very weird, and the sort of paradoxical weird nature of it is that once you then look at it, the wave function is said to collapse, and it sort of goes to one point, and then you can say, okay, yes, I have seen it and it has gone through this one slit, or the cat is dead or alive because you've seen it. So it's very weird in that it seems like an instantaneous moment. You go from a probability of anything happening to just one thing happening, and that's why it's very weird and quite hard to get your head around sometimes.
Yeah, I think actually there's a lot of like really good animations on like Schrodinger's cat on YouTube and stuff where people kind of like show it. One of my favorite memes on it is that one where it's the glass cupboard in the kitchen and the plates have fallen but they're leaning on it. It's like the plates are neither broken or safe because it's fine whilst the door is shut, but when you open you're going to have a conclusion kind of thing. But yeah, I find this one quite interesting, and the whole double slit experiment interesting in general, because it's just weird, isn't it? I mentioned this, I think, in the simulation theory episode. It's kind of like a game, you know, like when have you seen one of those videos before where it's like you're a little bit further out, it's kind of like in third person, but it's showing what like a first person game looks like. And when they're looking in that direction, it's like loading up, but everything behind them is black. And then when they turn, it's like a flashlight and it just loads the part of the screen that the character's looking at. And it's a little bit like that, isn't it? It's like the whole universe is existing in this probability field because it's probably better for energy. I'm sorry if that's wrong, but it's probably because it's like better than it deciding. But then when there's something there to observe it, it's like, well, we'll exist now kind of thing. It's like saving its RAM almost.
Yeah, it's such a weird thing in why does an observation do this? Why would that happen? Why is it not enough for it to exist probabilistically forever? And I think the weird thing is that ultimately, you know, we are all made up of quantum stuff. You know, we're all made of atoms, electrons, and stuff, but none of us behave quantumly. And yeah, I think I have discussed previously that they've done the double slit experiment on things about the size of viruses, so tens, maybe hundreds of nanometers in size, and you fire these at double slit, and you do get the quantum behavior, and they keep trying to make it bigger, but it's this sort of coupling of, you know, fundamentally everything has a quantum behavior, but when you put loads of them together, you just don't see it because it all washes out and averages out. So it's very difficult for us to get our head around that something that is so fundamental and is everything around us does something completely different to what we see. So.
Yeah. You know, when they say like being like an observer or being observed, is that like something conscious, or are they just talking about like light hitting something? So
way back in first year physics here. So in the mathematics, it's to do with this wave function, and when you observe it, the wave function, you apply something to it, a perturbation to it, basically. So this observation is just the act of the wave function being changed in some way. And yeah, that could be light. That there's no way around. It doesn't have to be conscious. It doesn't have to be anything. It just has to be observed, and it's to do with the sort of information that it is carrying. That is ultimately what this whole thing is trying to preserve. It's the information that it contains. Because if you start trying to find ways around that, then you can end up with things like fast and light travel, in which fast and light travel isn't prohibited because of the light itself. It's prohibited because you can't transfer information faster than that. So if you start messing around with it, this observation is basically the information transferring.
Is that like similar to like that whole quantum entanglement thing where you can like flip them and they can do it instantaneously, but they're not actually sending the data, they're just entangled?
Yeah.
Cool. And then is it, so it's kind of, so I think I've confused it actually. I think I've just confused with like the observable universe and light. So like the observable universe is everything light has touched. And the reason why you can't see outside of the observable universe is because light hasn't reached there yet from wherever it was coming from. Is it the Big Bang?
it's partly light hasn't. It's not so much light hasn't reached there; it's that light can't get from there fast enough to us.
Oh, okay. So it might have got there, but it hasn't come back.
Yeah. So this is so you have these very distant stars that are moving away. So this is going to sound really weird, but because again, nothing can move faster than light, but the space in between us is so big and expanding
Yeah.
that they are essentially moving away faster than the speed of light. So any light that they emit is not going to reach us because the space in between us is expanding faster than it can travel.
Right. So the observable universe isn't gonna like grow in size as like it's gonna get bigger, as in the light will travel further and we can see more. Everything is expanding from everywhere at once, so it will get bigger, but everything's gonna get further apart.
Mm-hmm.
So if you sent a human like past the line of the observable universe, is it basically impossible for them to ever get back because of expansion? Would they just kind of get lost out in there?
I really
okay.
don't
No,
know.
that's fair. This is the whole point of the episode. I'm planning on breaking everybody's minds, including the people that are listening right now. They're gonna be like, "Oh no, stop it."
The idea of the observable universe is very odd, and I don't think it's a concrete thing. It's just
Well, they're not even sure yet, are they? They're not sure yet if it's infinite or finite.
Mm-hmm.
Which is that's another fun one to get your head around. Like if it is infinite and you go left infinitely, you'll arrive back at where you started. Because my one question, right, is if it is infinite. Oh wait, no, I might have confused myself now. So if it isn't infinite, well, no, actually, if it is infinite and you go left and you'll end up back at where you arrived, does that mean eventually that the light or the energy from the Big Bang will come back round on itself? Or is that in a finite universe where it'll kind of come around itself? Because the way that I'd learned this, and I might be wrong, is you have to imagine the universe like a balloon, and you live on the surface of the balloon, and when you blow the balloon up, everything kind of just gets further from each other. But space is so big that we're not sure if it's, because we don't even know, we're not even sure on the shape of the universe, are we? Because I've seen something that people think it's like a Pringle.
Yeah, there's an issue of there's closed and open infinities. Something can be infinite but also be closed in that you can't. It sounds counterintuitive. Something can be infinite but you can't get out of it. So that's where like this idea of like things wrapping around in itself comes in. But there is also an open infinity in which things literally just do go on forever in every direction. So, and I don't think that's even decided. So
it's crazy, really. It's funny because our like main asset, I think, for the infinite void is like some wormhole thing that we've got. But no, that's it. These kind of things just blow my mind because for me, I get it. Like when I'm sitting at like a family event or something, if I start talking about this after a few drinks, it's allowed for maybe 20, 30 minutes. And then after that, people are like, shut up, Jake. Like you're hurting my head a little bit now. But like, I'm so like curious about the fact that we don't know what we're living in. That to me, these kind of things, I find so interesting. Like, I know it does hurt your head a little bit when you start thinking about like some of these things, and even like learning them as well is like a little bit mind blowing when you realize like how big everything is and how big our perception is of reality just here, when really it's like you're living on a grain of sand in the grand scheme of things. But yeah, I find all that kind of stuff interesting on whether or not it's infinite or finite. Another thing that I've been playing with too recently is I like fractals. I'm starting to think about the idea as well of like maybe like it's just fractal, like in both directions forever. Like maybe the better technology gets, we'll just keep zooming in. Like there'll be something past the quantum level, then something past that, and it'll just be like that picture that keeps zooming into the coast. And then like the same with zooming out. We'll zoom out and they'll be like, oh, there's a multiverse. And then they'll be like, oh, there's multiple multiverses. Oh, there's multiple multiverses. And maybe existence happens everywhere, but it's just on what plane of the fractal you live on when you're zooming in, and it's you have the same experience and existence, but it's just on whatever scale you exist on, and it goes infinite in both directions. But all that kind of stuff blows my mind. But that was a bit of a tangent, but kind of back onto the Schrodinger's cat. But basically, it's a thought experiment that was devised by the physicist Erwin Schrodinger in 1935 in a discussion with Albert Einstein to illustrate what Schrodinger saw as a problem to the Copenhagen interpretation of quantum mechanics. The scenario is often featured in theoretical discussions of the interpretation of quantum mechanics, particularly in situations involving the measurement problem. Schrodinger intended his thought experiment as a discussion for the EPR article named after its author Einstein, Podolsky, and Rosen in 1935. The EPR article highlighted the counterintuitive nature of quantum superposition, in which a quantum system such as an atom or photon can exist as a combination of multiple states corresponding in different possible outcomes. That was a mouthful, but yeah, I think it's a fun one, and I think it's a good one to kind of start on, because whenever you type in paradox, I feel like that's probably one of the first ones that come up. That and the grandfather paradox are the two that everybody always seems to kind of mention. But
yeah, it is an interesting one, and this is like fundamental in quantum mechanics, so good one to get us started.
Yeah, no, totally. So I'm excited to hear what this Hilbert / Infinite Hotel paradox is, because I've not heard of this one before, and I purposely didn't research it because I wanted to try and figure it out. Well, obviously I'm not going to figure it out, but I wanted to hear what you had to say.
So the Hilbert Hotel, so it's named after mathematician David Hilbert, who sort of came up with this, and it sort of carries on nicely from talk about infinities, in that it very nicely, it's a paradox in the way that it seems counterintuitive and sort of makes you think about what infinity is. And at the end, you'll see that there's different types of infinities, and that some are bigger than in others. And it shows that very clearly. So the Hilbert Hotel is this other thought experiment which says that there is a hotel with infinitely many rooms. So just imagine a corridor of rooms starting at room 1, 2, 3, 4, 5, etc. onto infinity. And every room in the hotel is full. So there's infinitely many people in the Hilbert Hotel. And then someone turns up and asks for a room. And this is the first sort of stage of it, is can you fit in the person? And intuitively say no. You say there's infinitely many people here. We can't fit any more in, but you can, because of the nature of infinity. All you have to do is just say to everyone in the hotel, move up one room. So room 1 goes to room 2, and room 2 goes to room 3, and etc. And you've got infinitely many rooms, so you can do that. And then you just slot someone into room 1.
Okay, yeah, that makes sense.
And you could do that with 100 people or 1 million people, as many people as you want, as long as you've got a finite amount of people turning up and asking for a room. You just shunt people along, and you can fit them in. So I think that makes a bit of sense. It's a bit weird to figure out infinitely many people like that, but it makes a bit of sense.
I can get behind that.
So what about if you want more people? So more than a finite amount of people turn up. So specifically, an infinitely long bus of people arrive at the Hilbert Hotel looking for a room. And can you fit them in? And how are you going to do it? So I think that one intuitively again feels like no.
Yeah.
This one feels like okay, right. I can see how you can maybe wrangle infinity to fit in a finite number of people, but there's no way you're fitting in an infinite amount of people coming off this infinitely long bus. But you can do it again very easily. All you have to do is say, you ask everyone in the hotel to go to their room number doubled. So room 1 goes to room 2, and room 2 goes to room 4, and room 3 goes to room 6. And suddenly you have infinitely many odd number rooms available. And again, you could just fit them in, and it's very easy to do it. So yeah, that's the second step. And then I think you can convince most people about we're somehow managing to fit an infinitely number of people into this infinitely large hotel. But then it gets weird in terms of even more people turn up.
Okay.
So your hotel is full, and then infinitely many, infinitely long buses decide to come along. And now you've got the problem of, okay, how are we going to do this? So there's still an infinite number of people, but following on from the last one, you said, okay, we managed to fit an infinite number of people in, but how can you do it this time? How can you organize doing this? So with before, you could just double everyone's room number, and then the person in seat number 1 on the bus goes to room number 1, and seat number 2 goes to room number 3, so the next odd number, and this works out. But now you've got infinitely many buses, so where do you even start with this? And there's 2 ways that you can think of this. The first way is to use the property of prime numbers. So when you take a prime and raise it to a power, so you do like 2 squared or 2 to the 3 or 2 to the 4, it's a property of primes that no prime to a power will be the same as any other, because it's a fundamental sort of property of numbers that they can't share a prime if they're made up of primes.
Yeah.
So that's what a property is. So 2 times 2 times 2 times 2 is never going to equal another prime times by itself any number of times. It's not going to happen because they're prime numbers. So one way of fitting all these infinitely many people on the infinitely many buses in is that you can take, so you've got everyone in your hotel, and you send everyone in the hotel to 2 to the power of their room number. And there's infinitely many rooms, so you can do that. So room 1 goes to 2 to the 1, so it goes to room 2. And room 2 goes to 2 to the 2, so it goes to room 4. And room 3 goes to 2 to the 3, so it goes to room 8. And this works. And then all you have to do is slot in the other primes. So for bus number 1, you take the person in seat 1, and that goes to 3 to the power of 1. And seat 2 goes to 3 to the power of 2. And then you do that for bus 1 infinitely many times. And then you go to bus 2 and take seat 1 5 to 1 number of times, and 5 to 2, and do that. So you could do it. And if you wanted to sort of put all this into a spreadsheet and try and get it to work, so Veritasium's got a great video on this. Is you can imagine having a spreadsheet where you have along your columns, you have room 1, you have 1, 2, 3, 4, 5, 6. So this is their room or hotel, their seat number, and then down the side you have the hotel, so people already in the hotel on bus 1, 2, 3, 4, 5. And you just fill in the spreadsheet with the infinite amount of people and the infinite rooms and infinite buses. And then you just draw a diagonal line that sort of zigzags back and forth, collecting everyone. And then all you have to do is take your diagonal line, stretch it out so it's straight, and then just put them into that room number. And this is a bit weird now, in that you're taking some sort of infinite line and stretching out infinitely many times to infinitely many rooms, but it works.
Solves the problem.
Yeah, so you can solve the problem with infinitely many buses of infinite length. So is there a case, and this is where the paradox sort of flips on its head, is there a way in which you can break the Hilbert Hotel, in which a number of people can turn up and you won't be able to fit them in? And there is. And the way to do it is, imagine a bus turns up where instead of people being sat in seat numbers, so you can use this trick of assigning people to seat number based on where they are, there's no seat numbers, so just everyone is stood up, just sort of mingling on the bus. It's like a party bus, and it's infinitely long, so infinitely many people. And it seems a bit weird because now you've just got one bus with infinitely many people on, but before you had infinitely many buses. But this breaks the system because there's no way to organize the people. If you try to, say, take a list of everyone on the bus, and everyone on the bus has a different name, so you have infinitely many combinations of names. So most people are just going to have random, infinitely long strings of letters, right? But they all have a name, they're all different, and they're all on the bus. So you have one person that's just called A, and one person called B, and one person which is called ABC, and then ABCD.
Yeah.
Infinitely many combinations, infinitely long. And it feels like you should be able to do it, but then just imagine that you've got your spreadsheet of all the names, and then you make a new name. So the new name, you take the first letter of the first person and change it to something else, and that's your first letter of the new name. And you take the second letter of the second person and change it, and that's your second letter of the new name, and so on. So you're basically going diagonally down the spreadsheet, taking the first entry for the first person, second entry for the second person, and just changing it to something else. Well, now you've got a name which you can guarantee is different from every name on the list in at least one letter, because you've changed every letter for one of all the names at some point. But your infinitely long bus has infinitely many names. So the name you've just created has to be on the bus somewhere, but they're not on your list. So this is the problem. There are people on your bus that are not on your list putting into rooms.
Right.
And this is sort of where this idea of infinity comes from, because before we were dealing with what's called accountable infinity. So you can count everyone on the infinite bus where there's seat numbers, and you can count everyone on the infinitely many buses where there's seat numbers. But this last case is what's called an uncountable infinity. There's no way in which you can count the number of people just by using their names that are infinitely long. There's no way you can do it.
That's interesting.
And it, just to sort of wrap it up, is this idea of countable and uncountable infinities. You can very, very easily prove using the same technique that there are more numbers between 0 and 1 than there are numbers from 1 out to infinity. The uncountable infinity between 0 and 1 is bigger than all of the real numbers that are countable infinity, because, again, you could write out all of your numbers and just... So all of your numbers between 0 and 1, so you have 0.1 and 0.12 and 0.9786, whatever, etc. And again, you can just change the digit of every number by 1 and create a new number that isn't on your list. So in summary, uncountable infinities are bigger than countable infinities, and it means that your uncountable number of people on your party bus can't fit into your countably infinite hotel. I realise I've just talked about
that was awesome. I have a question then. So obviously infinity is much more of a math thing than it is like I'd say a physical thing. But does that necessarily mean then that you would never be able to call something infinite, like you 100%, you wouldn't be able to call something infinite because, one, we can't count to infinity, and two, you wouldn't be able to see for infinity?
Yeah, I guess it goes back to your paradox of like the universe.
Is it more of a math thing than like a physical thing? Like the math is saying it, but we can't comprehend it or see it.
yeah, I guess in this case it's a mathematical trip of what we're saying infinity is. The numbers we have created. But there is, I think, a case here of it would be impossible to write a spreadsheet that is infinite.
Yeah.
Unless, of course, the universe was infinite and you could do that.
Yeah, because that's the other thing too, isn't it? It's like if the universe is infinite, then that would mean that there's like an infinite amount of energy and information to be able to do that task. But if it was finite, then you might not be able to tell if the universe was infinite or not, because there wouldn't be enough energy and information to replicate a universe.
Yeah.
That's
it's when you sort of start thinking about infinities in this way, it's very weird.
I'm surprised that it's took 40 episodes of The Infinite Void to talk about infinity. I just looked over then and I was like, I'm asking Matty like what infinity is, and I've just realized our podcast has got that word in it. But, no, that's cool. That's interesting.
Yeah. Hopefully, as I said, Veritasium's got a really good video on this. If you search Hilbert Hotel, for anyone that wants to sort of see this visualized, quite a good one. So.
All right. So my second paradox is the twin paradox. And essentially what that is in physics, the twin paradox is a thought experiment in special relativity involving identical twins, one of whom makes a journey into space in a high-speed rocket and returns home to find the twin who remained on Earth has aged more. And it's kind of all about this idea that was kind of in an Interstellar, and like this idea of if you can either get close to the speed of light or warp time through special relativity, you can kind of like change ages, even though people experience like the same time, well, the same thing in the same area. But yeah, it's interesting. It goes on to say that this result appears puzzling because each twin sees the other twin as moving, and so as a consequence of an incorrect and naive application of time dilation and the principle of relativity, each should paradoxically find the other to have aged less. However, in this scenario can be resolved within the standard framework of special relativity. The traveling twins' trajectory involves two different inertial frames, intral frames. I don't know what that word is.
I might be able to help you with this one.
Inertial frames, one for the outbound journey and one for the inbound journey. Another way of looking at it is by realizing that the traveling twin is undergoing acceleration, which makes him a non-inertial object. In both views, there is no symmetry between the space-time paths of the twins. Therefore, the twin paradox is not a paradox in the sense of a logical contradiction. But I find all these things kind of interesting. Like, was it Hawkins that said that he had a famous one, didn't he? I've gone too far trying to say what it was, but he had a famous quote or poem or something about somebody traveling at the speed of light, and she left, but she arrived the day before or something. And it was all about the idea of traveling away at great speeds or something, isn't it?
Yeah.
But special relativity and relativity I find fascinating too. I have like I treated myself to some layman books. You can actually see them in my webcam. They're there. But I've got like one on quantum mechanics, one on special relativity and stuff like that. And I'm working my way through them. But I find all that interesting, and I find it crazy as well how like Einstein predicted a lot of this stuff so long ago.
Yeah, I don't see how anyone would like
how do you know what I mean? Like it's hard enough to comprehend when like somebody's figured out the math for you. Do you know what I mean? Like it's just nuts that humans back in the day, without resources like the internet and stuff like that and technology, were like able to figure this kind of stuff out.
Yeah, it is pretty crazy. But do you want me to give you a quick explanation of the inertial frame?
Yes.
Okay, so this might give you a nice little starting point to go into the books a bit more. But the thing with the twin paradox, and I'm sure you've seen this, is there's this idea of one twin sort of flies out at near light speed or something, and then goes out somewhere and then flies back. And special relativity or general relativity, some relativity, people moving at speed experience time slower. That's the fundamental thing of it. But another thing of relativity is that you can't say it's that things are only relative to each other. So imagine me and you, we're stood together now, and I fly off away and then come back. The idea of relativity is that if this is done properly, there's nothing to say that actually I'm not the one that stood still and you're the one that's flying away from me.
Right.
That makes sense. So the paradox here comes from your perspective. I fly off really fast, come back, which means that I should experience time slower. So you aged 10 years, I aged 8 years. But from my perspective, you're the one that's moving. So you should age 8 years and I should age 10 years. So when we get back together and we're stood next to each other, who is older and who is younger? That's the paradoxical nature of this thing. That's basically what seems odd. But the inertial reference frame comes from the fact that this idea of things being relative is only applicable to something called an inertial reference frame. So that is where something is not accelerating, essentially. And the paradox is solved. So what I was talking about with non-inertial reference frames of the observer to the observer is that for me to fly off at light speed in one direction and then come back, at some point I have to accelerate. Not forget about the beginning and end point. That is an issue, but we can get around that. But just imagine that I am already moving and I fly past you, and we're starting the clock now. Oh,
yeah,
sorry.
That was quick.
For anyone watching on podcast here, I'm waving my hand around, but I'm already moving, so forget about that. But the problem is that at some point, a long way away, I'm going to have to slow down and then come back. And that acceleration there means that my reference frame is no longer inertial. So we can't do this trick of just saying, oh, either of us could be moving. We know which one of us is moving because I'm accelerating. Yeah. And that fixes it. So all of this sort of quickly untangles itself. And when we get back, you will find that I am younger than you, which is a weird result in itself if you don't sort of know about relativity. But you can do, we see this all the time with sort of spacecraft and stuff. If you send an atomic clock up and have it orbit very quickly, it will come back younger, so with less time than an identical clock that's just been sat on Earth. So the paradoxical nature is that's what the twins paradox is. And on first glance, you go, oh, that's weird. You have two people who are younger than each other at the same time, but it's to do with this relativity, and it sort of nicely figures itself out. Thanks, Einstein.
I think I've seen a video actually where somebody said that, like, if you had two people that wore watches and one went up like a really high mountain and the other one was like really, really low, over a long period of time, their clocks would be different.
Yeah. Yeah. So there is also things moving fast experience time slower, but also things near mass experience time slower.
Yeah, that's what Interstellar was on, wasn't it? When they were next to the black hole, like that planet, it was like 1 year was 7 years on Earth or something like that.
Yeah.
Don't they say as well, if you fell into a black hole and you were looking out of it, you would see like the universe's demise almost, like it aged completely as you're falling into it because of time dilation. People would see you just fade away onto the horizon, but you'd see like millions of years go by.
Yeah, I can't remember what happens from the perspective of the person inside. But if you were looking at someone falling into a black hole, I don't think you would ever see them disappear. They would just sort of vanish. You would never see them fall in. They just more slowly and slowly just fade away. But yeah,
they're cool.
it is an interesting paradox. It's quite cool. It's a paradox being solved, which is nice.
So what's your next one then?
So my second one is on something called the halting problem, or the decision problem. And I'll give a quick video shout out. So Tom Scott has a video on this in his, I think his series called The Basics on Computing, something like that, where he does a nice little graphic animated version of this. But the halting problem, interesting enough, it comes from David Hilbert again. This sort of starts this. So back at the end of the 18th century, there was, just for historical context, there was a big split in mathematics, with some people saying that, well, some of the infinities that we've been discussing just don't exist, can't be explained, and some people saying that no, maths is something that we can manipulate and do with what we want, and we can explain anything with it. And David Hilbert was in the sort of latter group, and he believed that maths was basically determinate in that you can determine whether any statement is true, is provable or non-provable. So using mathematics that was developed at that time, can you prove any statement? So you can sit down and, starting from the axioms of mathematics, so the very fundamentals, and David Hilbert does this in one of his books. I think he takes about 790 pages to show that 1 + 1 = 2. So it's not easy, and but you can show from the fundamentals. Obviously maths is arguably a man-made thing, but you can show from the fundamentals that 1 + 1 = 2. It's a provable statement. And likewise, there's certain things that we can show are non-provable. So this the sort of decision problem is can we determine, if you look at a problem, can you say for certain whether it is provable or non-provable? And fast forward a couple of decades to Alan Turing, he sort of tackles this problem from a sort of computing logistics point of view. So he says, looking at any code, looking at any computer problem, can you say whether the code will halt, so it will do something and get to an end solution? So that when you press your code, will it finish basically at some point? Or will it go into some infinite loop that it can't get out of? Is it non-solvable? And he invented a very simple device called a Turing machine. It's again a thought experiment, and this is basically, imagine an infinitely long tape of ones and zeros. So like the binary bits of code, infinitely long. You have a little read-write head. So your read-write head can read a bit, and if it wants to, it can flip it or change it. And then you give it some instructions or some code to do this. So you can say, if you see a 1, flip it. If you see a 0, just keep it the same. And that will basically go on forever, sort of thing, doing that. So this Turing machine, and any computer can be represented as a Turing machine. It is the most basic fundamental computer. If you wanted to, you could put absolutely any computer on a ridiculously long tape of ones and zeros and run it on a Turing machine if you wanted to. And he used this device to show that maths is not determinate. Is that you can't show this property of is something provable or non-provable for everything. So what he did was he said, okay, we're going to use the Turing machine. We're going to invent a computer that is able to do this. Let's not bother explain how it works, but you give it any code and it's able to say, yes, this halts, yes, this works, or no, this goes into a loop. And then on the end of that machine, we're going to bolt some sort of a flipping machine. So if the first machine halts, then the second machine does something which will create an infinite loop. And if the first machine goes into an infinite loop, it says this thing is an infinite loop. The second machine will halt. And you take both of these machines, stick them in a box as one machine, and you feed it its own code. So you feed it its own code that's able to determine if something halts or not. And what does it do? And this is like the classic paradox of, if it halts, then it determines that it doesn't halt. So it goes on forever. But that means that it doesn't halt. So it will halt. And that's the most fundamental type of paradox, in that something gets into a loop and it logically can't be solved. So Alan Turing, with this Turing machine that he devised, showed that maths is not determinate in this way. You can't, for any problem, for all problems, you can't just look at them and say, is it solvable or not? And that holds to this day. And for anyone interested about this sort of stuff, there's a lot of very abstract maths about what maths is, and if it sort of contradicts itself, and if it's complete, that you can do with this sort of stuff. And it gets quite interesting.
No, I bet. I'd never really thought about it, if I'm honest with you. And if I remember correctly, I think, was it the beginning of the year when that girl went viral, when she was asking people, like, how did we come up with math? Like, who decided what everything was, kind of thing, and how did it all just work out, and all this kind of stuff. And I was just like, yeah, that is kind of true. Like, it's cool that, because a lot of people say, don't they, that like math is like the universal language for the universe. And there's a lot, like we were mentioning earlier, even like with fractals, there's a lot of math in that. And everything really, as you were saying, can be described with math and stuff. But it's cool how like well it works, considering that we've created it.
Yeah, maths is very odd in how good it is.
Yeah.
And it is weird to think that, you do all these coincidences just sort of pop up places, like pi pops up in some thing of nature and all this sort of stuff, because we created it. Like we fundamentally wrote what it was. And like when back in the beginning of the end of the 18th century, when this sort of debate was happening, so it was a big debate about set theory. So part of the debate was, can everything be put into a set? And this is where the sort of contradictions came in. Is, okay, well, the set of everything, does that include itself? Because if not, that means that there is there is something that is not in the set of all sets. And this sort of contradiction. And we solve this by saying that the set of all sets is not a set. And that's... and we could do that because it's maths, and we could do what we want. So.
No, it's cool. I rate that. No, I rate that. So some honorable mentions, and I thought I'd chuck these in because on Twitter this week I asked our listeners. So if you're not following us, head over to @InfiniteVoidPod on both Instagram and Twitter. But I was basically asking people on social media what their favorite ones were. And the three that we got one was the grandfather paradox, which, if I'm right in saying, is, if I go back and kill my granddad, how did I go back to kill my granddad? Because I don't exist in the first place to go back. But I'm pretty sure either through string theory or something else, they've got a answer for that. Isn't it? If you go back in time, hypothetically, then you're not going back in time. That's your current time, and everything after that becomes your new time. So, like, your granddad exists. Yeah. He created you. So you go back in time and say kill your granddad. It doesn't wipe you from your timeline. It just creates a new timeline where you've gone back and killed your granddad.
Yeah, there's a few different ones where like you don't really go back in time, you just continue forward, but almost like rather than you going back, your granddad comes forward,
Yeah.
and you kill a future version of your past granddad, that sort of thing, or you do go back in time, but then you don't return to the same timeline. You go off in a new timeline. There's another one with superposition where you have this sort of superposition of your granddad not existing and existing sort of thing. So I think there's a fundamental problem here going back in time,
Yeah.
whether that's possible. But and that I think that does sort of solve the paradox. If the paradox can't physically happen, I think we can safely say it isn't a paradox.
I tell you what, actually, I'm reading Brian Greene's new book. I can't remember what it's called now, but it's something to do with like time dilation and stuff. And he blew my mind because he was breaking down like they're pretty confident that the science is there to go forward, aren't they? But they don't know how you can come back. They're like, we're pretty sure like through like tricks of math and like going near heavy objects and stuff, we can go forward into like you could speed up time relative to you, but there's no way to get that back. Like if we sent you 1,000,000 years into the future, you can't ever come back if you don't decide you like it. You're just stuck 1,000,000 years in the future.
Yeah,
but it's
so I think that one has some solutions.
Yeah,
if it can exist.
And then another one that was quite popular was the Fermi Paradox, which we've done an episode on. There are so many planets in the universe. Why haven't we seen life yet? And it always falls back to: is it hard for life to be created? Are we the first to the party? Are we the last to the party? Has everybody wiped themselves out with a great filter? But that one's always a fun one to play. And then another interesting one, which I hadn't really heard much of until I researched this week, but it's Olber's Paradox. And it's essentially the idea of why is the night sky dark if there is an endless, uniformal, like, amount of stars giving out light.
Yeah, I hadn't heard of it referred to as Olber's Paradox. I hadn't heard of that, but I think I actually stumbled across it earlier in that this idea of the observable universe. It's not, and we say here, when you look out and every line of sight must eventually terminate as a star. Well, maybe, but those stars are moving faster away than the light can get to you. So
true.
I think that one also has a solution.
True. So yeah, actually, so then would Olber's Paradox. So then maybe when the Big Bang happened, maybe at the start of time, the night sky would have been light. Because everything would have been close together, right? But like now, because everything's moved too far apart. So so eventually then, obviously, because we don't know what's going to happen, if the universe just lives on for infinity or if it has a big crunch or whatever it's going to be, that heat death or whatever it is. But so does that mean eventually then that like there won't be any stars in the night sky because they'll all...
Yeah, that would be a part of the heat death scenario. Everything just drifts apart, that we don't see anything. So
nice. Cool. That's interesting.
We had to ruin it at the end.
And then obviously another little one, which I would say it's kind of in the area, but at the same time, I didn't really want to call it a paradox, but I thought I needed to mention, and that was just free will, which is an interesting one. I'm surprised we haven't done an episode yet on free will. I'm sure that we will in 2022, but yeah, that's another thing that I've been getting interested in. Brian Greene was kind of breaking it down in his new book, and it was really because he takes the stance that it does not exist. He's like, free will is not a thing. He was like, you're made up of a soup that the universe decided that's what life is, and those atoms and those things were probably always going to have that in their like timeline, basically. Like that electron from the beginning of time was always going to end up becoming a part of you and your consciousness, and the decision that you've made, you've not made because that was just all of the atoms acting in the correct laws of physics in the environment kind of thing. So everything's just playing out because it should be playing out and all this kind of stuff. And I thought it was really interesting because I find free will a fun one. because I like applying it in the aspects of like religion and stuff. Because for me, it's like, say if there is a creator, if there is a creator, then you could make the argument that maybe free will doesn't or does exist, because if he's giving you free will, then you can make your own decisions. But if there wasn't free will and there was a creator, then why would you be given like the feeling of free will? So I find that a fun topic of conversation. I know you kind of align on the idea of non-free will, don't you?
Yeah, I think we did mention it very briefly, is that ultimately things seem to be either fundamentally random, so at a quantum level with the probabilities things are random, that's what they do. Or you could say, okay, no, things are just deterministic and just play out as they were always meant to do. Yeah. And neither of those I don't see any way in which either of those give rise to free will. So
yeah, no, that's fair. That's fair. I find it interesting, but I'm sure we'll do it. We'll do a big episode on free will at some point, because I think that was one of the main ones I think that was one of the first things you suggested, wasn't it? When we like first got together, that was like one of the 5 that you wanted to do. So I'm sure we'll do that. But yeah, appreciate everybody tuning in this week. Happy Halloween, everyone. Enjoy the last of spooky season. It's always a fun time. I get really annoyed though, man. The last 2 Halloweens I've been moving, so I don't like get to fully experience like the decorations and everything, because we have to like pack everything up. But yeah, have a great Halloween, everyone. If you enjoyed this episode, make sure you give it a like. If you've got another paradox that is your favorite and you think we should have mentioned it, let us know down in the comment section below. If you're watching on YouTube, hit that subscribe button, because we're coming up very quickly on 200, and it'd be awesome if you guys could help us get there. If you are a listener and not a watcher, then go and subscribe to YouTube, because it's free and it'll just help us out anyway. And if you haven't hit the follow/subscribe button on your choice of audio platform, then do that now too, because it helps us out. And yeah, guys, we will catch you next time for the conclusion of our Humanity of the Future series. It's quite insane how long it is. I was saying to Matt that it's we started it in May and it's coming up on November, so it's been a very long time. But we're going to finally conclude that, and then I'm sure there'll be a new poll on social media for whatever series you guys want us to do next. But yeah, thank you so much for tuning in this week, and we will catch you in the next one. Hey everyone, we wanted to take a moment to tell you about our brand new Patreon page.
Yeah, so we've devised a load of new goodies that are neatly packaged across 3 different tiers for you.
Tiers start at £3 and go all the way up to £10 a month.
Just to say, the Patreon is in no way an obligation, and we're going to continue making the podcast as it is, freely available across all the platforms. But if you'd like to support us and show your support, you can now.
So yeah, head over to patreon.com/Infinite Void Pod for more information.